Imagine unrolling an old document and seeing a tangle of ink, abstract lines, colored patches, and strange markings that seem to lead nowhere. This is the visual outcome of a complex problem, compressing the three-dimensional curves of our planet onto a flat sheet. For centuries, navigators and explorers have used these flat representations to cross oceans and map the unknown. Geography creates a shared system of measurement, translating the chaotic physical features of Earth into organized, reliable data. Finding your way requires understanding the specific components that make the system work: orientation, scale, and symbols. Once you understand how these elements function together, you can pinpoint exactly where you are standing on the planet. The most accurate model of our planet is a globe. Because it shares the Earth's spherical shape, it preserves the true surface area and distance of every continent. However, a globe is physically bulky. It cannot be folded into a pocket or easily carried on a hike. This practical need for portability led to the invention of flat maps. Converting a sphere into a flat rectangle is a mathematical struggle. It's like peeling an orange and trying to force the skin to lay perfectly flat on a table. That stretching creates unavoidable distortion. Land masses near the poles are pulled apart to fit the edges of the map, which is why Greenland often appears as large as Africa, even though Africa is actually 14 times its size. While flat maps sacrifice total accuracy, they provide the local resolution needed to navigate a specific city or a single street. Every functional map starts with the compass rose. This graphic establishes north as a fixed point, allowing you to orient the paper with the physical ground beneath you. Then there is the scale bar. This acts as a translator for distance, showing exactly how many real-world kilometers are represented by a single inch of paper. The legend identifies what the colors and shapes represent, differentiating between a mountain range, a metalled road, or a river. Maps are built for specific tasks. Physical maps highlight natural terrain, political maps define borders and capitals, and thematic maps display localized data, such as rainfall patterns or population density. By combining these three elements, direction, scale, and symbols, we can model any environment on a single sheet of paper. These tools work on land, but how do you navigate a featureless space like a desert or the open sea? We use a grid system. Latitude lines run horizontally around the globe. They originate at the equator and define global climate zones, separating the tropical torrid zone from the temperate and frigid regions. Longitude lines are the vertical meridians that run from pole to pole. They meet at the top and bottom of the Earth, providing the east-west component of the grid. Where these lines intersect, they create a unique coordinate pair. New Delhi, for instance, is physically located where the 29th north latitude line meets the 77th east longitude meridian. This invisible mathematical matrix assigns a unique, searchable address to every square inch of the Earth. These longitude lines serve a second function. They define global time. Because the Earth rotates 360 degrees every 24 hours, the planet turns exactly 15 degrees every 60 minutes. Countries choose a standard meridian to keep their clocks consistent. India uses the 82.5-degree east line, which places Indian Standard Time 5.5 hours ahead of Greenwich Mean Time in London. In the digital age, satellites handle this math for us. GPS receivers use signals from space to calculate our exact coordinates in real time. This satellite system is the backbone of modern navigation, but it depends on a clear line of sight to the sky. If you lose signal in a tunnel or a dense forest, an analog map remains the only reliable way to find your position. Whether you are using a phone or a paper map, these coordinates and symbols are the essential system we use to navigate the physical world.